So this is question 13 from the trial exam. It came from paper 2 2020, question 11 on that paper. And we have figure 2, it's a modulus graph. The equation's given, and we have to find the coordinates of P. There's various ways of thinking about this. One of the ones I like to consider, which will also help us later on, is to think about the transformations it would take to get us to this graph in the first place. So what I mean is, if we consider just x plus 4, for example. So if we draw the graph of y equals x plus 4, I'm just going to sketch it on here like so. So we'll have the y-axis up there, the x-axis. And if I want to sketch y equals x plus 4, we know it's got a gradient of 1 and it's going to pass through the y-axis at 4. But if I want to change that into a modulus graph, okay, when I get to the x-axis, okay, which is going to hit the x-axis at -4 when y equals 0. To change that to a modulus graph by putting a modulus sign around it, I know that it's now going to bounce off because the modulus function instantaneously makes all negative values positive. Now, that's the first instance. Now, the second instance would be if I want to perform a vertical stretch. So suppose I want to sketch this function where we take the modulus of x plus 4 and we double our y values. Now, when that happens, we're going to get this kind of thing happening. So it's going to still be intersecting the x-axis at -4, where the inverted apex is, but it's now going to be cutting the y-axis at 8 because all the y values have doubled. Okay, so that's important to consider. Now, for the final transformation, which is going to look like this, so it's going to be a translation parallel to the y-axis. Now, if I subtract 5 from all of those values, and I'm going to do that just by dragging this graph down, I have to subtract 5 from every single y value. It's going to drop the graph down by 5 units. So my y-intercept is not going to be at 8 anymore. It's now going to be at 3. So I've got to drop it down. So if I move it down by about 5 units, and because I did it in 2 pieces, I'll have to do it like that. So it's going to look like that. And if I just redraw it, so it's going to be something like this, just so it matches the color I've chosen. Okay, so it's going to look something like that. Now we can see that the y-intercept is now at 3, and this apex still at -4 because we haven't done anything in the x direction in terms of transformations, but the y value is going to now be at -5, and that's where the point P is. Okay, so it's quite nice to consider it in terms of transformations because we also get the y-intercept as well. So I can now label P as -4, -5, and my y-intercept at 0, 3. That might be useful later on. So for part B, we have to solve this equation. So let us consider this graph, y equals 3x plus 40. Now, the right-hand side of this equation is the modulus graph in the diagram. If we just have a look at this for a second, the y-intercept is much, much higher or much, much greater than our modulus graph. So the modulus graph has a y-intercept at 3, 40, obviously 37 units higher than that. So that's going to put it off the scale. Now, it also has a gradient of 3, which means it's steeper. So just to give you an indication, it's going to look something like this. I'm going to try and draw it on here. So it's going to do something like that. In fact, that's not very good. Let me try again. Maybe something like that. So hopefully you can tell the orange line that I've drawn which corresponds to y equals 3x plus 40, is steeper than the positive branch of the modulus graph. Now it has to be because the positive branch of the modulus graph has a gradient of 2. We know that because of the transformations that we performed earlier. We took x plus 4, we took the modulus of that, which means it has a gradient of 1 on the positive branch. We then doubled everything, which means it has a gradient of 2. Now, this means that if you have a gradient of 3 compared to a gradient of 2, they will not intersect. Okay, you can tell from the diagram. The only place that they will intersect is on the negative branch, somewhere around here. Okay, and to give us an indication of that, if we just find out where 3x plus 40 crosses the x-axis, it's going to be when y equals 0. So it's going to be at negative 40 over 3, which is about negative 13, just a bit more than that. So it's going to be somewhere slightly greater than negative 13. How do we do this? Well, let's have a look at the equation of the negative branch of our modulus graph. There's various ways of doing it. One way is to consider the modulus and how it turns anything that's negative into positive. So for the negative branch, our equation would look like this. We would have 3x plus 40, and that would equal 2. Now, I can remove the modulus sign, and because it's the negative branch, it has to have a gradient of negative 2. So everything inside the modulus will now be multiplied by minus 1. Okay, because the modulus will make everything x plus 4. And then we subtract 5. That's one way to do it. Another way to do it is just to piecemeal kind of build the equation yourself. So this gradient is going to be negative 2. Okay, because it's a mirror image of the positive branch, and it's passing through negative 4, negative 5. So if we use y equals mx plus c, very quickly, we would see that negative 5 is equal to negative 2 times negative 4 plus c, which means that I'd have to add 8 to both sides, which would be, no, that's wrong, sorry, beg your pardon. I would have to subtract 8 from both sides because we have a double negative. So that would be negative 13 is equal to c. Okay, and that would give me an equation of y equals negative 2x subtract 13, which is the equation of that branch. And I know that because that negative branch passes through P at minus 4, minus 5. Just to corroborate that, over here, we have 3x plus 40 is equal to negative 2x, subtract 8, subtract 5. So on the right-hand side, you can see we have exactly the same result as I found earlier. We just have to solve it now. So let's add 2x to both sides. We have 5x is going to equal negative 53. Dividing by 5, so that's negative 53 over 5, which is negative 10.6. Okay, so that's the equation solved. There's only one solution because the gradients diverge. Now, for the final part of this question, we're told we have this line L, which has a gradient of A. And more than that, it doesn't have a positive or negative y-intercept. It actually passes through the origin. Okay, it's just y equals ax. So that tells us something important, that it passes through O. So let's just indicate that on our diagram here. That's where L passes through, because it doesn't have a plus C that we can say anything about other than 0. Now, we're told that L intersects our modulus graph at least once. Thinking carefully about this, we know that our line L cannot be parallel to that positive branch. Okay? If it was parallel, like the diagram I've just shown you here, there's going to be 0 points of intersection. So we have to consider what would happen if we rotate L about the origin, which is what we're going to have to do if the gradient is a variable at the moment. We know it's a constant, but it can vary because we're going to have to find a range of values. So one option would be the following. So we could have our L like this. So this would be at 1 point of intersection where it would just intersect the modulus graph here at P. Okay, that would give you 1 point of intersection. Now that would make the gradient at this point somewhere less than 2. I don't quite know what it is, but it's got to be less than 2 because I've made it less steep. By making it less steep, it's caused an intersection with that apex point at P. Now, if you remember from earlier, we found that P was at the point -4, -5. So this tells us something important about this gradient of our line y equals ax. So in terms of distances, we have 5 units down, 4 units across. Okay, so we know, yes, A has to be strictly less than 2, otherwise we won't have any points of intersection. But we have now just deduced that A has to be less than or equal to 5/4. Okay, when A is equal to 5/4, we have 1 point of intersection, okay, at P. Okay, so that would be at P. So I might as well state that. I hope that makes sense. All right, so that's one condition. Now there is another condition. Okay, if we make A obviously strictly less than 5/4, we're going to have 2 points of intersection, because as you can see, if I just make A a little bit less steep, it passes through the modulus graph twice. Okay. All right, and it's going to do that no matter how shallow we make it until we get to 0, and it will still obviously be passing through at 2 points. So we need an upper bound for this. Now, for the upper bound, let's just remove some of this so we can see what we're doing. Now, we can't have it parallel, but one thing we can do, if we go beyond parallel, make it a little bit steeper, the line y equals ax is going to do something like that. Now, that will create another point of intersection further up, okay, which we can see here. Okay, and as I make A steeper and steeper, as it approaches infinity, I'm still going to have 1 point of intersection, and I have to have at least 1 point of intersection. So what is the condition for this? Well, I just have to think about what I've done. I've said that A has to be greater than 2. Okay, now is that enough? Well, yes, because as you make the line steeper, a vertical line parallel to the y-axis has a gradient of infinity. Okay, so it has a limiting behavior. If you make A greater than 2, it will cover all possible eventualities. So to conclude, we have A has to be strictly greater than 2, because we can't have it equal to 2 because that would be parallel and there would be 0 points of intersection. But we also have to have A to be less than or equal to 5/4. Okay, so we have to write this in set notation. So the two conditions are any value A such that A is greater than 2. That would be your first set. Okay, then we also have A such that A is strictly less than, no, sorry, I said that wrong, less than or equal to 5/4. And you can have either of those intervals, so we put a union there to represent or. So those are the ranges of values for A.